Hello, can everyone hear me? I'm going to be continuing from my last stream. I'm going to be studying C++, chapter 20. Okay, so it's only a last few sections of chapter 20. Hold on. Okay, so chapter 20, I was reading this and I ended it at introduction to lambdas. I'm going to be rereading ellipses and I will finish these three chapters. Hopefully, it would be within 1 hour, but I'm expecting a 1 hour stream. Ellipses, I invite to avoid them. I read this last stream, so I will just reread this again. The argument list is one or more function parameters. Functions that use ellipse take this form. So return type function name argument list and then ellipses. Note that functions that use ellipses must have at least one non-ellipsis parameter. Any arguments passed to the function must match the argument list parameters first. So in example, double find average in count. Let's just try that. CST, CST CSTD CSTD. Then we have ellipses. So we access the ellipses via a VA list. So let's declare one. So std VA list. And this gives the list of ellipses. So VA start. First, we have to include a CSTD arg header. The header defines VA list, VA arg, VA start, and VA end, which are macros that we need to use to access the parameters that are part of the ellipses. We then declare a function that uses the ellipses. Remember that the argument list must be one or more fixed parameters. In this case, we are passing in a single integer that tells us how many numbers to average. The ellipsis always comes last. Note that the ellipsis parameter has no name. Instead, we access the value of ellipsis through a special type known as a VA list. It is conceptually useful to think of VA list as a pointer to that points to the ellipsis array. First, we declare a VA list, which we have called list for simplicity. Okay, so they've done that over here. And first argument is list to initialize. The second argument is the last non-ellipsis parameter. So they're putting the values of this in here. And the second argument is like which parameter is the last one. So if you have like count and then count 2 would be over here. The next thing we need to do is make list point to our ellipsis parameter. We do this by calling VA start. VA start takes two parameter, the VA list itself and the name of the last non-ellipsis parameter. Okay, and then arg is list. VA arg is how you get the argument. So the list and then the data. Then if we call VA arg again, we get the next item in the ellipses. To get the value of the parameter that VLS currently points to, we use VA_arg. VA_arg also takes two parameters, the VA list itself and the type of parameter we are trying to access. Note that VA_arg also moves VA list to the next parameter in the ellipsis. Yeah. Finally, to clean up, when we are done, we call VA_end with VA last as a parameter. Hold on. Why ellipses are dangerous? Type checking is suspended. Ellipses offer the program a lot of flexibility to implement functions that can take a variable number of parameters. However, this flexibility comes with downsides. With the regular function parameters, the compiler uses type checking to ensure the types of the function arguments match the types of the function parameters. This helps ensure you don't pass a function an integer when it is expecting a string or vice versa. However, note that ellipses parameter have no type declaration. When using ellipses, the compiler completely suspends type checking for ellipses parameter. This means it is possible to send arguments of any type to the ellipses. However, the downside is that the compiler will no longer be able to warn you if you call the function with ellipses argument that do not make sense. When using the ellipses, it is completely up to the caller to ensure that the function is called with ellipses argument that the function can handle. Let's look at an example of a mistake that is pretty subtle. So 6.1.0, this here is a float, a double actually, but interpreting as an integer will give like something else. Although this may look harmless at first glance, note that the second argument is a double instead of an integer. This compiles fine, but produces a somewhat surprising result. A variable's type tells the compiler how to translate the sequence of bits into meaningful value. However, you just learned that ellipses throw away the variable's type. Consequently, the only way to get a meaningful value back from the ellipses is to manually tell VA_arg what the expected type of the next parameter is. This is what the second parameter VA_arg does. Okay. Hold on. If the actual parameter doesn't match the expected type, bad things will happen. In the above program, we told VA_arg that our variable are all expecting to have a value of int. Consequently, each call of VA_arg will return the next sequence of bits translated as integer. In this case, the problem is that the double we passed in as the first ellipsis argument is 8 bytes, whereas VA_arg list int will only return 4 bytes of data with each call. Consequently, the first call to VA_arg will only read the first 4 bytes of the double, and the second call to VA_arg will read the second 4 bytes of the double. Thus, our overall result is garbage. So, does that mean like this last value is not read if this is read twice? Not only do the ellipses throw away the type of the parameters, it also throws away the number of parameters in the ellipses. This means we have to devise our own solution for keeping track of the number of parameters passed into the ellipses. Typically, this is done in one of three ways. One is pass a length parameter. I think this is what we are doing here. So 5 is basically count. Use a sentinel value. A sentinel is a special value that is used to terminate a loop when it is encountered. For example, with strings, a null terminator is used as a sentinel value to denote the end of the string. Okay, over here they're using the sentinel value of -1. So arg is -1, then break. There are a couple of challenges here. First, C++ requires we pass at least one fixed parameter. In the previous example, this was our count variable. In this example, the first value is actually part of the number to be averaged. So instead of treating the first value to be average as part of the ellipsis parameter, we explicitly declare it as a normal parameter. Okay, so they have a separate parameter just for the first value. Second, this requires the user to pass in the scintilla value as the last value. If the user forgets, the function will loop continuously until it runs into a garbage that matches the scintilla. Use a decoder string. Method 3 involves passing a decoder string that tells the program how to interpret the parameters. Oh, so I, integer, 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 integer. Okay, so it's looping through the string, and the type depends on what you define. I think this is the best option. The decoder string can be a bit cryptic, and if the number or types of optional parameters don't match the decoder string precisely, bad things can happen. First, if possible, do not use ellipses at all. Oftentimes, other reasonable solutions are available, even if they require slightly more work. For example, in our find average program, we could have passed in dynamically sized array of integers instead. This would have provided both strong type checking while preserving the ability to pass a variable number of integers to be averaged. Second, if you do use ellipses, it is better if all values passed to the ellipsis parameter are the same type. Intermixing different types vastly increases the possibility of the caller inadvertently passing in data of the wrong type and VAR producing a garbage value. Third, using a count parameter decoder string parameter is generally safer than using a sentinel value. This forces the user to pick an appropriate type for the count decoder parameter, which ensures the ellipsis loop will terminate after a reasonable number of iterations, even if it produces a garbage value. Okay, so let's run this program. This floating thingy over here, previously I made it through Godot, but I updated it. I remade it using Raylib in C. So if anyone wants their own like desktop pet, just let me know. Three and 3.5. Yep, that's correct. So it works properly. If we don't call v end, would that be okay? Consider this snippet of code we introduced in 18.3 contains nut. So string.find nut, string view no position. Okay, so if there is a position, then it will return true. This code searches through an array of strings, looking for the first element that contains the substring nut. Thus, it produces the result found walnut. Okay. So, auto found std find if array begin till array end. Getting find if, and we are using this function. If found is equal to array end, then no nuts. Else found, and then the value of found. The root of the issue here is that std_find_if requires that we pass it a function pointer. Because of that, we are forced to define a function that's only going to be used once, that must be given a name, and that must be put in the global scope. The function is also so short, it's almost easy to discern what it does from one line of code than from the names and comment. A lambda expression allows us to define an anonymous function inside another function. The nesting is important as it allows us both to avoid namespace naming pollution and to define the function as close to where it is used as possible. Syntax for lambdas is one of the weirder things in C++ and takes a bit of getting used to. Lambdas take this form: capture form, parameters, return type statement. What is this capture clause? So putting the square brackets is like how you tell the compiler that this is a lambda. Capture clause can be empty if no captures are needed. Or what do they mean by captures? The parameter list can be empty if no parameters are required. It can also be omitted entirely unless a return type is specified. The return type is optional, and if omitted, auto will be assumed. While we previously noted that that type deduction for function return type should be avoided, in this context it's fine to use. Also note that lambdas have no name, so we don't need to provide one. A lambda with an omitted return type, no captures, and omitted parameters. Let's rewrite the above example using a lambda. So find if, and then you define, wait, this is confusing. So constant expression std array string view. Define the function right where use it. So we have array begin, array end. Here no lambda capture clause. I don't know why I like it when the if is in like the same line. So here's a lambda expression string view string return string dot find nut. It's not equal to no position value. I think it's better if this is on the next. I think it's more readable. It's like this. This works just like function pointer case and produces an identical result. Notice how similar a lambda says to a contains a nut function. They both have identical parameters and function bodies. The lambdas has no capture clause. We will explain what a capture clause is because it doesn't need one. We have omitted trailing return type in the lambda for conciseness, but operator not equal to returns a poll. Let's see. So it should be mentioned. I'm guessing like this, right? Bool. Let me see. Yeah. So if I run this, found walnut. Well, what is the type of lambda is even? What do they mean by this? Wait, I skipped a few things. In the above example, we define a lambda right where it was needed. This use of a lambda is sometimes called a function literal. However, writing a lambda in the same line as its use can sometimes make code harder to read. Much like we can initialize a variable with a literal value for use later. We can also initialize a lambda variable with a lambda definition and then use it later. A named lambda along with a good function name can make code easier to use. For example, in the code snippet, we are using std all of to check if all elements of an array are even. So return all of begin and integer I. So we are running this function with all of the array elements and checking if they all return true. We can improve the readability using this. Instead, we can store lambda in a named variable and pass it to the function. But what is the point of making it anonymous now? Can't we just define a function as even? As it turns out, lambdas don't have a type we can explicitly use. When we write a lambda, the compiler generates a unique type just for lambda that is not exposed to us. In actuality, lambdas aren't functions, which is part of how they avoid the limitations of C++ not supporting nested functions. There is a special kind of object called a functor. Functors are objects that contains overloaded this operator that can make them callable like a function. Although we don't know the type of a lambda, there are several ways of storing a lambda for use post definition. If the lambda has an empty capture clause, nothing between hard brackets, we can use it as a regular function pointer. Std function or type deduction via the auto keyword will also work. So int main, you have double, double, double. Add numbers 1 and 2. So this is add numbers 1, a regular function pointer. This is add numbers 2, std function. So I'm guessing this helps nesting a function. We are defining these function inside of main. The lambda could have non-empty capture clause. So std function pointer using auto stores the lambda with its real type. The only way of using the lambda's actual type is by means of auto. Auto also has benefit of no overhead compared to std function. What if we want to pass a lambda to a function? There are 4 options. Case 1, use a std function parameter. So int repetition, const, std function void int. Use a function template with the type template parameter. Okay. Case 3, use the abbreviated function template syntax. Okay, case 4, use function pointers only for lambda with no capture. So lambda int I. Okay, I understand case 1, case 2, case 3. Okay, I understand this one. Okay. I kind of understand, but I need more practice with them. In case 1, our function parameter is std function. This is nice because we can explicitly see what the parameter and return type of std function are. However, this requires the lambda to be explicitly converted when the function is called, which adds some overhead. This method also has the benefit of being separable into a declaration and a definition, if that's desirable. In case 2, we are using a function template with type template parameter t, When the function is called, a function will be instantiated where t matches the actual type of the lambda. This is more efficient, but the parameters and return type of t are not obvious. In case 3, C++20 is auto to we use C++20 is auto to invoke the abbreviated function template syntax. So case 3, okay, they're using this. This generate a function template identical to case 2. In case 4, the function parameter is a function pointer. Since a lambda with no capture will implicitly convert to a function pointer, we can pass a lambda with no captures to this function. For most part, lambda parameters work by the same rules as regular function parameters. One notable exception is that C++14. Since C++14, we are allowed to use auto for parameters. In C++20, regular functions are able to use auto for parameters too. Wait, what do they mean by this? When a lambda has one or more auto parameter, the compiler will infer what parameter type are needed from the calls of to the lambda. Because lambdas with one or more auto parameter can potentially work with a wide variety of types, they are called generic lambdas. When used in the context of a lambda, auto is just a shorthand for template parameter. Let's look at a generic lambda. So std array months, pre C++17 use std array const character 12. So search for 2 consecutive months that start with the same letter. So find adjacent month begin, month end. Make sure that the 2 months were found. And std next returns the next iterator after same letter. So what does same letter return? Like if a and b match it, this function will return true. So std adjacent find will return a, is what I'm guessing. Or pointed to a. In the above example, we use auto parameter to capture our strings by const reference. Because all string types allow access to their individual character via square bracket operator, we don't need to care whether the user is passing in std string, c style string, or something else. This allows us to write a lambda. We could expect any of these, meaning if we change the type of months later, we won't have to rewrite the lambda. However, auto isn't the best choice. Consider std array months, const auto 5-letter months. Count if months begin, month end. There are 2 months with 5 letters. And how is it returning true? So count if returns how many times we get true. In this example, using auto would infer a type of const character pointer. C such strings aren't easy to work with. In this case, we prefer to explicitly define parameter as a string view. Or they're defining the parameter string view over here. and previously it was a const auto reference. So here const character reference. As of C++17, lambdas are implicitly const expression if the result satisfies the requirement of a constant expression. This generally requires two things. The lambda must either have no captures or all captures must be constant expression. The functions called by the lambda must be constant expression. Note that many standard library algorithms and math functions won't make constant expression until C++20 or C++23. In the above example, a lambda would not be implicitly const expression in C++17, but it would be in C++20. This means in C++20 we can make 5-letter months constant expression. Generic lambdas and static variables. In lesson 11.7, we discussed that when a function template contains a static local variable, each function instantiated from that template will receive its own independent static local variable. This may cause issues if that is not expected. Generic lambdas work the same way. A unique lambda will generate for each different type that auto resolves to. The following example shows how one generic lambda turns into two distinct lambdas. So algorithm array IOStream string view. So print hello, print world. So auto print. Following example shows how one generic lambda turns into two distinct lambdas. Static int call count. So call count plus plus and then value. Where are two distinct lambdas? Oh, because auto value first it was like first this was string, that's a separate lambda function, and then it was integer, that's a separate lambda function. In the above example, we define a lambda and then call it with two different parameters. This generates two different versions of the lambda. Most of the time, this is inconsequential. However, note that if the generic lambda uses static duration variables, those variables are not shared between generated lambdas. We can see this in the example above, where each type has its own unique count. Although we only wrote the lambda once, two lambdas were generated, and each has its own unique version of call count. To have a shared counter between two generated lambdas, we have defined a global variable or a static local variable outside of the lambda. If return type deduction is used, a lambda's return type is deduced from the return statement inside the lambda. All return statements in the lambda must return the same type. So int, boolean, auto divide. No specified return type. So return type is int. Error return type doesn't match the previous return type. This produces a compile error because the return type of the first return statement doesn't match the return type of the second return statement. In the case we are returning different types, you have two options: to explicitly access a cast to make all return types match, or explicitly specify a return type for the lambda and let the compiler do implicit conversion. The second case is usually the better one. So we have double, they explicitly mentioned double. This would be converted to a double. For common operations, you don't need to write your own lambdas because the standard library comes with many basic callable objects that can be used instead. These are defined in the functional header. So std greater std array, so sort, and then std greater. No need for curly braces to instantiate object. Lambdas and algorithm library may seem unnecessarily complicated when compared to a solution that uses a loop. However, this combination can allow some very powerful operations in just a few lines of code and can be more readable than writing your own loops. On top of that, the algorithm library features powerful and easy to use parallelism, which you won't get with loops. Create a struct student that stores the name and points of a student. Create an array. Wait, so they want type def struct struct student uh, std string name and integer points. Is this correct? Create an array of students and use std max element to find the student with the most points. Then print the student name. Integer main return 0. So given the following array, we have these arrays. Let me think. And then use stdmax to find the student with the most point. Std cout. Okay, I have no clue how to do this. Let me think. Hmm. They said max element. And then I guess array dot begin, array dot end, and then std greater. No, we use the student function. Hold on. So we are comparing the points and we return the name of the student. So let's do std string view best student name. Let's see. I have no clue how to do this. STD string view. So student. Let's see. I think we have to do it. We are comparing two students, right? Student, and then if student one dot points is more than actually return student two dot points. If student one's point is bigger, then student one dot name. Otherwise, student two. I thought it copied the whole thing. Student two dot name, and the return type is std string string view. Let's see if this works. So stdo best student name. Cannot convert this to std string view. Std sort. Wait, how did they use the lambda function again? With comparisons. Auto better student comparator is this anonymous function. And then over here, better student comparator. I don't understand this error. Initializing cannot convert whatever this is to std basic string view character. Where is this? So line 29. What's the type of the they do auto, right? I don't think we should call it string view. I think we should call it auto. Auto. Let's see. On line 32, operator, right hand operator of type. I think it has to be like this, maybe. PD reference it. Yeah. STD array iterator. So how do you print it? Let's try this. This is an iterator, right? So it should be maybe dot name. Maybe like that. But shouldn't this return a boolean then? No, it should return the student. String std string return 5. I have no clue. Maybe I think it returns the student. Perhaps. Static cast convert cannot convert student to boolean. This is line. Hold on. think I just need this maybe. And then it will be assumed to be Boolean. Francis has the lowest score. So it's like this. Right. Dan is the high score. Okay, now it works. So I'm guessing how a max element works is that compare student 1 and student 2. If it's true, then student 2 is the current marks. If it's false, then student 1 is the current marks. And then it takes the winner from here and compares with Christine. If this is true, then Christine is the current marks, and if it's false, then the previous winner is current marks. Okay, let's see how they did it. So you have string view, name, and integer points. So instead of string view, now we don't need this. Did we use include algorithm? I don't think we did. Okay, apparently they did. Where did we use include algorithm? Is it std max? Yeah, I think it's in algorithm. Oh yeah, and I can use the other syntax. Best student name. For some reason, the previous syntax actually seems easier for me. Oh, this is the hint. Then this is the actual solution. So max elements. Use std sort and a lambda in the following code to sort the seasons by sending average temperature. Program should print winter, spring, fall, summer. Okay, so let's copy this. Let's see. So a struct season int main. Okay, so they want us to use std sort over here. What is this then? Oh, I see. So auto seasons. No, wait. Std sort is like inline, right? Std sort. Isn't it just this? seasons. How does the function work? I forgot. Std sort. I don't want to look at the answer, but why isn't the sort like highlighted? Okay, let me guess. Is it like seasons and then the lambda? So lambda season S1 and then season S2 and then return S1 dot average temperature is less than S2. So the previous average temperature should be less than the next average temperature. Is this correct? I don't know why there's no like the reference for sort. What's the issue? Season. Maybe it's this. Expected three arguments. No matching overload. Wait, when I press control click, it doesn't. Maybe it's like seasons dot begin and seasons dot end. Yeah, I think this is it. Winter, spring, fall, summer. Winter, spring, fall, and summer. Next chapter, lambda captures. This is the question I was repeatedly asking. In the previous lesson, we introduced this example. Example banana, watermelon, lemon, and find if, find for string, find for nut. Let's modify the nut example and let the user pick a substring to search for. This isn't as intuitive as you might expect. So search string value, search for search rather than nut. Find if, search. This code won't compile. Unlike nested blocks, where any identifier accessible in the outer block is accessible in the nested block, lambdas can only access certain kinds of objects that have been defined outside of the lambda. Oh, so search over here. Search is defined over here, but it's not defined within the lambda. Objects with this includes objects with static storage duration. This includes global variables and static locals, and objects that are constant expression. Since search fulfills none of these requirements, the lambdas can't see it. Lambdas can only access certain kinds of objects that have been defined outside the lambda. This includes objects with static storage duration and objects that are constant expression. Since search fulfills none of these requirements, the lambda can't see it. To access search from within the lambda, we will need to use a capture clause. The capture clause is used to indirectly give a lambda access to variables available in the surrounding scope that it normally would not have access to. All we need to do is list the entries that we want to access from within the lambda as part of the capture clause. In this case, we want to give our lambda access to the values of variable search, so we add it to the capture clause. Okay. So like this basically. So how do captures actually work? While it look like our lambda in the example above is directly accessing the value of main search variable, this is not the case. Lambdas might look like nested blocks, but they work slightly differently. When a lambda definition is executed for each variable that the lambda captures, a clone of that variable is made inside the lambda. These clone variables are initialized from the outer scope variable of the same name at this point. Thus, in the above example, when the lambda object is created, the lambda gets its own cloned variable named search. This clone search has the same value as the main search, so it behaves like we are accessing main search, but we are not. While these clone variables have the same name, they don't necessarily have the same type as the original variable. We'll explore this in the upcoming section of this lesson. The captured variables of lambdas are copies, not the actual variable. Although lambdas look like functions, they're actually objects that can be called like functions. When the compiler encounters a lambda definition, it creates a custom object definition for the lambda. Each captured variable becomes a data member of the object. Captures are treated as const by default. When a lambda is called, operator bracket is invoked. By default, this operator treats captures as const, meaning the lambda is not allowed to modify it. In the following example, we capture the variable ammo and we try to decrement it. So shoot ammo, decrement ammo. STD view ammo, shots left. And then when they call shoot, they're checking how many shots are left. The above won't compile because ammo is treated as a const within the lambda. Mutable captures. To allow modification of variables that we captured, we can mark lambda as mutable. So ammo mutable. Now mutable, we are allowed to modify ammo now. While this now compiles, there's still a logic error. So 9 shots, 8 shots, 10 shots left. 9 shots. So when shooting, stdcout is within the lambda function. So lambda function is called. 9 shots left. Shoot again. 8 shot left. But the outside, because this over here is a copy of this. When the inner one changes, the outer one remains the same. When the lambda was called, the lambda captured a copy of armor. When the lambda decremented armor from 10 to 9 to 8, it decremented its own copy, not the original armor value in main. Note that the value of armor is preserved across calls to the lambda. Because captured variables are members of the lambda object, their values are persisted across multiple calls to the lambda captured by reference. Much like functions can change the value of arguments passed by reference, we can also capture variables by reference to allow our lambda to affect the value of the argument. To capture a variable by reference, we prepend an ampersand to the variable name in the capture. Unlike variables that are captured by value, variables that are captured by reference are non-constant unless the variable they're capturing is constant. So capture by reference should be preferred over capture by value. Okay. Ammo, the reference to ammo. Ammo is captured by reference and then minus minus ammo. Now let's use a reference capture to count how many comparisons std sort makes when it sorts an array. So std string view make, std string view model, comparison sort begin end, comparison so possible output comparisons to. Okay. Capturing multiple variables. Multiple variables can be captured by separating them with a comma. This can include a mix of variables captured by value or by reference. So int health 33, int armor 100, c enemies, health armor and the reference to enemy. Having to explicitly list the variables you want to capture can be burdensome. If you want to modify your lambda, you may forget to add or remove captured variables. Fortunately, we can enlist the compiler's help to auto-generate a list of variables we need to capture. A default capture captures all variables that are modified in the lambda. Variables not mentioned in the lambda are not captured if a default capture is used. To capture all used variables by value, use a capture value of this. To capture all used variables by reference, use a capture value of this. Here's an example using a default capture by value. So with height, std cout, cin width and height, find if as begin, areas end, will default capture width and height by value. Because they're mentioned here. Oh, and if they use an ampersand, they will capture all the values by reference. Default captures can be mixed with normal captures. We can capture some variables by value and others by reference, but each variable can only be captured once. Okay, so this is by default equal, otherwise reference, capture by reference for enemies. And over here by default reference, otherwise capture by value for armor. Illegal, we already said we want to capture everything by reference. Illegal, we already said we want to capture everything by value. Illegal, armor appears twice. Illegal, the default capture has to be the first element. Defining new variables in the lambda capture. Sometimes we want to capture a variable with a slight modification or declare a new variable that is only visible in the scope of lambda. We can do so by defining a variable in the lambda capture without specifying its type. So main std array areas. We store areas but use the user entered width and height. We need to calculate the area before we can search for it. Declare a new variable that's visible only to a lambda. The type of user area is automatically reduced to int. User area will be calculated once the lambda is defined. The calculated area is stored in the lambda object and is same for every call. If the lambda is mutable and modifies a variable that was defined in the capture, the original value will be overridden. So int known area return user area is equal to known area. Wait, I don't understand. So okay, so we are inputting width and height. The user is going to input the width and height, and the width and height will be assigned to user area. The type of user area is automatically reduced to int. Okay. So this variable is only visible inside lambda. Int known area. So these are the known areas. Oh, and then it checks if any of the known areas is equal to the user area. Okay, I guess that makes sense. User area is only defined once, and it's checking with and comparing with each one. Variables are captured at the point where the lambda is defined. If a variable captured by reference dies before the lambda will be left holding a dangling reference. For example, returns a lambda auto make walrus. Capture name by reference and return the lambda. I am a walrus and my name is name. Create a new walrus whose name is Rufus. Say name is the lambda returned by make walrus. So auto say name make walrus Rufus. Wait, hold on. So make walrus Rufus returns this anonymous function, which is stored in say name. Then call the lambda function that makes make walrus returned. So we are calling this function. I'm a walrus. My name is. Oh wait, the reference for this is lost when this statement. So over here we are getting the reference to string, but after this executed, this Rufus over here is stored in a temporary variable, right? So after this statement has finished executing, the reference to this is lost. The call to make Rufus makes a temporary std string from the string literal Rufus. The lambda in make walrus captures the string temporary string by reference. The temporary string dies at the end of the full expression containing the call to make walrus, but the lambda say name still references it past that point. Thus, when we call say name, the dangling reference is accessed, causing undefined behavior. Note this also happens if Rufus is passed to make walrus by value. Parameter name dies at the end of make walrus, and lambda is left holding a dangling reference. If we want the captured name to be valid when the lambda is used, we need to capture it by value instead. Because lambdas are object, they can be copied. In some cases, this can cause problems. Consider the following code. So count I. So they're capturing I and then stdi plus plus. invoke count, and then auto other count, create a copy of count, invoke both count and the copy. This outputs 1, 2, 2. So 1 for this, uh, 2 for this, and 2 for this. Rather than printing 1, 2, 3, the code prints 2 twice. When we created other count as a copy of count, we created copy of count in its current state. Counts I was 1, so other counts I was 1. I see. So I here, when count runs, I becomes 1, oh, inside here. And then when we are copying when the I is 1. So this count as I 1 plus 1, and then this other count as 1 plus 1. So they both return true. Both return 2. Let's look at a slightly less obvious example. So my invoke function. So const std function void function, run the function, increments and print a local copy of I. So auto count I, mutable, my invoke count, my invoke count. Wait, so this over here is a reference, right? But it's all printing 1, 1, 1. When we call my invoke count, the compiler will see that count which has a lambda type doesn't match the type reference parameter std function void. It will convert the lambda into temporary std function so that the reference parameter can bind to it, and this will make a copy of the lambda. Thus, our call to fn is actually being executed on a copy of a lambda that exists as part of the temporary std function, not the actual lambda. We need to pass a mutable lambda and want to avoid the possibility of inadvertent copies being made. There are two options. One option is to use non-capturing lambda instead. In the above case, we could remove the capture and track our state using a static local variable instead. But the static local variable can be difficult to keep track and make our code less readable. A better option to prevent copies of a lambda from being made in the first place. But since we can't affect how std function are implemented, how can we do this? One option is to put our lambda into std function immediately. That way, when we call my invoke, the reference parameter fn can combine to std function and no temporary copy is made. Or instead of auto, we did std function, increments and print a local copy. Our output is now is expected, so 1, 2, and 3. An alternative solution is to use a reference wrapper. C++ provides a convenient type as part of the functional header called std reference wrapper that allows us to pass a normal type as if it was a reference. For even more convenience, std reference wrapper can be created by using stdref function. By wrapping a lambda in std reference wrapper, whenever anybody tries to make a copy of a lambda, they will make a copy of reference wrapper instead. Here's our updated code using stdref. So stdref. What's interesting about this method is that it works even if my invoke takes fn by value instead of reference. Okay. Which of the following variables can be used by the lambda in main without explicitly capturing them? Try to use the variables without explicitly capturing them. So B, C, D, F, G, H, I, J. Which of the following variables can be used by lambda without explicitly capturing them? So B can be used because it's constant expression. C can be used because it's static. Therefore, D, G, and H, and J as well. And maybe I, I'm not sure about I. So A, no, has automatic storage duration. B, yes, constant expression. C, yes, static storage. D, I said yes to this. E, yes, E is usable in a constant expression. Oh, so E is included as well. F, no, because get value. G and H, I'm guessing yes. G and H, yes. I is a global variable. J is accessible in the entire file. What does the following code print? Don't run the code, work out in your head. So favorite food, grapes. Auto print favorite food. STD, see out. I like grapes. So favorite food, bananas with chocolate. So I'm guessing it will print I like grapes. Yeah. Favorite food, capture favorite food by value. Modifying main's favorite food doesn't affect lambda's favorite food. You're going to write a little game with square numbers, numbers which can be created by multiplying itself. To set up a game, ask the user to enter a number to start at. Ask the number how many values to generate. Pick a random integer between 2 and 4. This is a multiplier. Generate the number of values the user indicated. Begin with the starting number. Each value should be the next square number multiplied by the multiplier. Play the game. The user enters a guess. If the guess matches any generated value, the value is removed from the list and the user gets to guess again. The user guesses all the generated values, they win. If the guess does not match a generated value, the user loses and the program tells them the nearest unguessed value. So ask the user to enter a number to start at. Hold on. So stdcn and starting num. And then std cout where to start at. Ask the user to guess how many values to generate. How many values to generate? Pick a random integer between 2 and 4. This is the multiplier. So what the programmer picks? I generated 5 square numbers. Do you know what each number is after multiplier? "32, 72, 50, 126 wrong. Try 128 next time. I don't understand what the game is. Starting at 4, the program generates the next 5 squares. 16, 25, 36, 49, 64. Pick a random integer between 2 and 4. This is the multiplier. Okay, let me just do int multiplier is 4. Starting from 4, the program generates the next 5 squares. 1, 2, 3, 4, 5. Start where, how many? Wait. So std array int and starting num how many. Std cout. Wait, how do we check the size of the array? Array dot it was that length and capacity thing. Start with vectors only. Let me think. For int I is 0. So I'm going to fill this array with these many numbers. I is less than how many, and then I plus plus. Starting at 4, the program generates the next 5 squares. Okay, hold on. So starting num array I is equal to starting num times it by itself, and then starting num plus plus. Okay, let's test this. Size how many? A variable with non-static storage duration. Cannot be used as a non-type argument. Okay, wait. How do you like initiate an array that can I and how many can I do this? Okay, let's see. Let's just use a std vector. So start, count, multiply random.get. I generated count square numbers. Do you know what each number is after multiplying it by multiplier? Oh, so you don't store it in an array? They do actually. Numbers, std vector int, static cast std size t count. Oh, they're generating it like this. They are using std vector. Can I define the size at the start? How do I do that? Is it this? Or its size like a get function? No, I think size is a get function. Now let's see. Way to start at 3. How many values to generate? 4. And then I get 25. I think, wait, let's try this. Conversion from int. I might have just done this as unsigned. Conversion from int to const unsigned 64. Unsigned sign mismatch. And then I should do it from the very start. Unsigned int. Sign unsigned mismatch how? Line 14. I guess I will do this on side as well. Five values to generate. Let's do 4. 25, 36, 49, 54, 64. So, and then what they want? Pick a random number between 2 and 4. This is the multiplier. Generate the number of values the user indicated. Begin with the starting number. Each value should be the next square number multiplied by the multiplier. So now the int multiplier is, let's say, 2, and then multiplier. I still get confused with the random std random thing. Include random.h. Use random.h to generate. Oh, this is their own. Okay, let's forget random.h. Let's just put our own function, put our own random number. Multiplier, undeclared identifier. Start at 4, generate 10. Let's see, 32. So 25 times 2 is 50, right? And now they have to guess it. The user enters a guess. If the guess matches any generated value, the value is removed from the list and the user gets to guess again. The user guesses all of the generated values, they win. If the guess does not match a generated value, the user loses and the program tells them the next unguessed value. Wait, we can just do all of that over here, right? So 4 numbers left, 3 numbers left. Do you know what each number is after? Hold on. Do you know what each number is after multiplying it by let's see. Array guess the next number. Std cout square numbers. Actually, let's start with starting num square numbers multiplied with multiplied, I think it's by, right? By multiplier. Now you need to guess these many square numbers multiplied by this, and then let's see. Int guess stdcn guess. We don't even need this vector. Okay, but let's just have it. And num is and maybe we should do it over here. Yeah, we should do it over here. Okay, so take the guess. You need to guess these many square numbers multiplied by this multiplier. So std cout your first guess, and then guess If array dot at I is not equal to guess, if it is equal to guess, then you guess the next number. Bool pass is true. But you assume that fail is false, and then you turn the fail to true. Else uh, you should have guessed this next time, and then break. Actually, let's do pass. Pass is true, and then if they fail, do pass false. Uh, if pass std cout, you win. Let's see. Guess, guess the next number. Hold on. Let's do this. Uh, if I is less than how many? So if there are still some more i's remaining, then we tell them to guess the next number. How many? I think we should do how many minus 1. Hold up. I don't think this is the right way. Let me do it anyways. But if I want to test this, I want to know what the answers are. Then I'll just std cout answer dash 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 std cout std cout and answer dash dash dash. Okay, let's see. Okay, way to start at 4 and generate 10. Right, these are the answers. So now I'm like, pretend I don't know this. I'm guessing, what's the answer? Let me guess 32. Your next guess 50. Guess the next number 72, 98, and then 122. You should have guessed 128 next time. Guess the next number should be like this. Hold on, unsigned int I, which would be 0. And there should be a while loop. I is less than how many while I is less than how many. And then over here you do I plus plus. This doesn't make sense. No, this does make sense, but like actually I should just do this. If I is more than 0, and then guess the next number. Five, 4. So 50, 72, 98, 128. First guess 50, next guess 72, 98, 128. You win. Then if I run this again, the only thing that's difficult is like I don't understand the random part. So I will say way to start at let's say 3, generate 5, and then 45. You should have guessed 18 next time. Yeah, I think this is how we do it. Now, why would we remove the number from the array? Generate the values the user indicated beginning with the starting number. Each value should be the next number. multiplied by the multiplier. So the game works. Okay, anyways, let's just read the summary and quiz. Let's just finish this. The next chapter is so long, I don't know how many streams it's going to take. Function arguments can be passed by value, reference, or address. Use passed by value for fundamental data types and enumerators. Values can be returned by value, reference, or address. Function pointers allow us to pass a function to another function. Dynamic memory is allocated on a heap. Cursor function is a function that calls itself. Command line arguments allow users and other programs to pass data into a program. Ellipses and lambda function. Write function prototype. A function named max that takes two doubles and returns the larger of the two. Write function prototypes. A function named swaps that swaps two integers. Or is they are taking the addresses of x and y. Function named get largest element that takes the dynamically allocated array of integers and returns the largest number in such a way that the caller can change the value of the element returned. Okay. Dynamically allocated array of integers. Okay. And returns the largest number in such a way that the caller can change the value of the element returned. Also, you're returning the reference. What's wrong with these programs? Do something. 1, 2, 3, 4, 5, array 3. We are returning the pointer. Do something returns a reference to a local variable that will be destroyed when do something terminates. So sum to value and then sum to value. Oh, there's no base case, so it's an infinite recursion. Float, divide, then divide. Oh, the two divide functions are not distinct. So when you're calling this, the compiler doesn't know which one to use. Int main array. Oh, there's the memory in this stack is very small. This is going to be a problem. Array argv1. Shouldn't it be a pointer to char? Is this correct? Wasn't it pointer to wasn't it like an array of strings? So it's like pointer to char. Argv is a string argument and can be converted to an integer via assignment. So the issue is here. The best algorithm for determining whether a value exists in a sorted array is called binary search. Okay, how long is this? Okay, I think I will end this stream here. I'll just read about binary search and then I'll end the stream. Binary search works as follows. Look at the center element of the array. If the center element is greater than the target element, discard top half. If the center element is less than the target element, discard bottom half. If the center element equals the target element, return the index of the center element. If you discard the entire array without finding the target element, return the center element that represents not found. So, given an array and a target value of 7, at first, min 0, max 8, because we are searching the whole array. The array length is 9, so the index of the last element is 8. We calculate the midpoint, which is 4. Element 4 has value 12, which is larger than our target value. So discard this half of the array and search this half, and then you do half of 4, which is 2, and so we are now searching, looking at this, which has 6. Element 1 has value 6, so discard 3 and 6, and then the next element is 7. Okay, I'll end the stream here. At the next stream, I might either do math or I will continue with C++. I'll see. Anyways, see you next time.